In this video, we are going to look at multiplication rules and conditional probability. Now the logic is going to get a little bit deeper, and you're going to have to pay a little bit more attention than in the last video, which dealt with classical probability. Now, what I have on this page is a contingency table, also known as a two-way table, that gives cross-classified data. And all the boxes within the table are known as cells. And for example, I have this table here, which is a cross-classification of US hospitals of varying type, and along with the number of beds. So I have 5 types of hospitals, H1 through H5, a general, psychiatric, chronic, tuberculosis, or other type of hospital. And the sizes of beds, B1 through B3, are small hospitals with under 24 beds, medium-sized hospitals with 25 to 74 beds, and larger hospitals with 75 or more beds. Each column total is the total of number of beds, or total of number of hospitals with that number of beds. And each row total is the total number of hospitals with those designations. And in the bottom right corner, you can see that 6,580 hospitals were identified here. Now, in this next example, part A and B, we are going to first begin by describing events in words, just as we had done before, and then we are going to move on to computing probabilities. So let's start here with describing H2. H2 means we're choosing a psychiatric hospital, and that's exactly what I've written over here. Now, if I move down to computing the probability of a psychiatric hospital, choosing that at random from all of the hospitals, that will be this 737 that you see there out of the 6,584 in the bottom right corner. And I could reduce the fractions or attempt to, or put them in decimal form. But for right now, I'm going to keep it in this format so that you can see specifically where these numbers come from inside of those tables. Now, B2 refers to a column. That's the medium-sized hospital, or choosing a hospital with between 25 and 74 beds. If I want to know what is the probability of choosing a hospital with 25 to 74 beds, you can see that there are 2,010 of them total out of the 6,580. And that is the fraction that I have listed there. And this time I did reduce it. When we have the AND symbol, and it's referring to these tables, it actually tells you to go into a particular cell. When we are dealing with H2 and B2, I'm saying anything here, H2 is in the H2 row, and the B2 is the B2 column. Now, AND refers to overlaps. The probability, well, first off, let's describe it. H2 and B2 is in the overlap there, and that is a hospital that is a psychiatric hospital with between 25 and 74 beds. Now, the probability there says, let's go right into that cell where the 242 is, and the probability will be 242 out of the 6,580. Now, if I'm dealing with the word or, I'm not looking at just the overlap. I'm basically dealing with all of the hospitals in row H2 or column B2. Okay, I'm dealing with choosing a psychiatric hospital or choosing a hospital with 25 to 74 beds. And sometimes these events that are described with the word or just are sometimes kind of clunky, as we saw back in the previous video. Now, when I'm looking to find the probability, I have to add the probability of H2, the row total, and the column total together but subtract off those 242 hospitals that were counted both with the row and with the column. And you can see that I've done that there. I've added the row and the column together. I subtracted off the 242. I put parentheses around the numerator just to remind you that if you're doing this on a calculator and turning it into a decimal, you need to have parentheses around the numerator. And we have a reduced answer there of 501 out of 1,316. Now, this was a frequency distribution in the table that we had at the left. Over at the right, it's asking for something different. It's asking for a joint probability distribution. Now, I'm not interested in filling in this whole grid because it will take quite a while, but all of these are going to be filled with probabilities. Now, notice that in the bottom right corner, we have this 1 standing for 100%. If I were to take every value in that table at the left and divide it by the number 6,580 in the bottom right corner, that would, in that right corner, give you the 1. If I want to know what number is in that top left cell, basically that would be the 260 that we had over in the frequency table divided by the 6,580. And we would have to divide for each of the cells by that 6,580 to get all of the probabilities filled in. Not a task we want to do. And we'd have the choice of leaving it as a fraction or as a decimal. Okay, now we're going to move on to conditional probability. I need you to understand that when you write P parentheses A with that vertical bar in there and the B, that vertical bar is pronounced given. Okay, and you have a formula here, but I never use this formula. Okay, basically you take events A and B, you find their intersection, the probability of it, and then you divide by the probability of the second number in that parentheses, which will be the denominator. Now, I don't do it that way at all, as you will see. I have an example for you. And this example, again, is rolling a die. Now, what we're going to do here is define events. And we're not defining any events yet. We're going to say probability of A and B. That A, we said again, that bar was to be pronounced as given. I'm going to have event A being rolling a 3 and event B be rolling an odd number. Now, we've already done parts of this already. It's only the bottom 2 parts that are new. So probability of A, probability of rolling a 3, you know that that is 1 out of the 6 outcomes, and there's our answer, 1 out of 6. Probability of rolling an odd, a 1, 3, or 5. We know that that is 3 of our 6 outcomes, which reduces to 1/2. A and B says find the overlap of being a 3 and being an odd, which is just being a 3, and that probability is 1 out of 6. For the probability of A or B, we say, let's find the probability of the 3. Okay, that is 1 out of 6. And then we look at the probability of an odd, and basically we're looking at A, joining the 2 together, which 3 is consumed within the category of an odd. So basically there are 3 possibilities here, and we will say 3 out of 6 reducing to 1/2. Now, all of that to get down to these bottom 2 parts. In this P of probability of A given B, I'm asking what's the probability of A given that an odd number is rolled. In other words, I've rolled a dice and I go, hey, here's a secret. It's not any old number. I've rolled an odd number. Given that it's B, I've told you it's a 1, a 3, or a 5 that I rolled. I've given you some extra information, so it's no longer out of 6. I have given you some information. It's out of those 3 possibilities, 1, 3, or 5. Now, what's the probability of a 3? Oh, that's 1 of those 3 values. That is a lot easier to figure out than to break out a formula. The next one says, what's the probability of B given A? In other words, I start with the given information. Psst, I rolled a 3. It is a 3 that I rolled. Now that you know it's a 3, what's the probability I rolled an odd number? What's the probability of B? Well, if I rolled a 3, it is odd. It's guaranteed that I rolled an odd number, and for that reason, the probability will be 1. Okay, I have a probability distribution listed here for a previous Congress, and we're going to be choosing one person at random from that Congress. So let's do this. What is the probability that the person we chose is a senator? Now that is a column we're looking at, and I'm going to go straight down to the column total, 0.187. And that will be the answer there. It already contains the probabilities within this table. Is a Republican senator? Well, that actually says find the overlap of being a senator and being a Republican, and it takes you right to the position that I have my mouse in, which is 0.103. Now we get into a little bit more involved calculations. Is a Republican, given that he or she is a senator? I'm going, psst, hey guys, it's in this second column. I know I can't say it's out of 187 people, but let's pretend it's 187 people. How many of those 187 would be Republicans? Oh, that would be 103 of them. So we basically ignore the decimal and treat that as 103 out of 187. And if you remove those decimals, technically move 3 places to the right, that's like multiplying by 1,000 in both the numerator and the denominator. There's your answer. Now I'm reversing the order of the sentence. Now I'm saying, what's the probability the person I choose is a senator, given that he or she is a Republican? I'm going, psst, hey guys, we're in that second row. I'm telling you it's out of those values there. Now I know there's not 527 people, but I'm basically in that row. And if that was a whole number, what's the probability that now that you know it's out of those 527, that it's a Republican, or given that it's a Republican, what's the probability it's a senator? The answer will be 103 out of that 527. And that's what I have right there, 103 out of 527. You always need to look for the words given that. The phrase given that will help you to identify what the denominator is, or in the case of this problem, which row or column that you are in. It narrows down the probability as if I'm going, hey, here's a hint for you. It changes the denominator. Now, if we were in the classroom, and we're not, we would be doing an example right now where I would pretend that we're going out for a meal together, and you get to go choose a shake perhaps at a restaurant to have. And I would take a survey of you in terms of, hey, who wants what flavor? And we're going to classify it by gender. So I've already made up the data here for you, and I filled some numbers into this table, and you're going to want to pause the video in a little bit because I'm going to tell you, hey, we've got 18 people we've surveyed in this class. The class is partway through. We've lost some people so far. And out of those 18 people, here are how many people wanted each of the flavor. We are going to now select a person at random. So C will stand for chocolate, S will stand for strawberry, etc. And I'm asking you to find each of these probabilities. For example, let me just begin with the first one before you pause your video. What is the probability of a female? Oh, I look at this and I say, females, there are 12 of them out of the 18 people in the class. So we will say the probability is 12 over 18. And because you've got the ability on your calculator to reduce fractions, we're going to write that as 2 over 3 reduced fractions. We're going to leave all of these as fractions for this problem. So if you could pause the video now and do these as best as you can, based upon what we've just learned, in this chapter, and then we'll check the answers in a little bit. Okay, let's move on and look for P of C. That's the probability that the person wanted chocolate. 8 people, that was the row total, wanted chocolate out of the 18. So we will write 8 out of the 18 people. Both of those numbers are even, so that will reduce to 4/9. Now, when I move to vanilla and male, I'm going right into a particular cell there, the cell that has the 2 and refers to the intersection, or where did the row and the column overlap, and we're right there with those 2 people. So 2 out of 18 will be that probability. For the next one, oops, and that will reduce to 1/9. Now, these next 2 are very related to each other. What's the probability the person wanted chocolate given that they were female? If I say given that they're female, I'm telling you that the person came from the female column. I'm telling you it's out of those 12 people. Out of those 12 people, how many wanted chocolate? Answer, 5 out of those 12. So that is going to be 5/12. Now, when I move on to female given chocolate tells me that it will be in that top row, which contains 8 people. So it will be out of 8. How many are female? Answer, 5. Let me erase my circle, and that will be 5 out of the 8, which is already reduced. Moving on to the next column, S and F, someone who wants strawberry shake, and is a female. That's the overlap of that row and that column, and that's where the 4 in this table is. 4 out of the 18 people, and 4/18 is going to reduce to 2/9. Now, V or F says the person either wants vanilla or is a female. Well, vanilla, we had 5 people wanting vanilla, or turns into addition, and we have 12 women. But there are 3 women who wanted vanilla who were already counted among the vanilla people and among the females. That's the overlap that needs to be subtracted off. And then this will all be out of 18. So we get 14 out of 18, and that is going to reduce to 7/9. Chocolate or male. Chocolate, okay, we've got 8 people in that row. Male, we have 6 people in that column, but there was an overlap of that row and column, which contained 3 men who wanted chocolate. So I will subtract those 3 off, and we will get 11 out of 18. Now we move back onto some more conditional probability problems. What's the probability that the person wanted vanilla given that they were female? I'm telling you, given they were female, it's in this column. It's out of those 12 people. How many wanted vanilla? 3 out of those 12. So our probability is 3/12, which reduces to 1 out of 4. Male given chocolate. Okay, I'm telling you we're in the chocolate row. Psst, here's that information. It's not out of 18, it's out of that 8. What's the probability the person wants male? 3 out of those 8 people, and that does not reduce. Okay, vanilla and female says find the overlap of those 2 conditions, that row and that column, and that's where we see the 3 out of 18. So 3/18 will then reduce to 1/6. Chocolate or female. Chocolate, we have 8 people who wanted chocolate in that row, plus we had 12 women in that survey. Now, if you were to go and add across and forget the subtraction, you would say, ooh, that's 20 over 18, and you can't have a probability that's over 1. So that would actually be a clue to remind you that you have to subtract off the overlap of chocolate and female, which is those 5 people. And that will give us 15 over 18, which reduces to 5 over 6. We have male or strawberry. Male is 3 in that, sorry, let's try that again. Male, we have 6 in that column. Strawberry, we have 5 in that row. And the overlap of male and strawberry is 1 person. So I will subtract that 1 person out, and we will get 10 over 18, which reduces to 5 over 9. Probability of just strawberry. Oh, that's just a row total. I slipped that in there as kind of an easy one. 5 out of the 18 people. That's all we're looking for. And then male and chocolate goes right to that top left cell and says find the overlap of those 2 conditions. So I've got 3 people in that intersection out of the 18 people in that chart, which gives us 1 out of 6 as a probability. That is a great problem to practice with, to drill yourself on. Go back, reprint out the notes, try those again, and come back and check with the answers that you've taken down here, because this type of problem is very easy for me to put on a test. It's easy for you to look at the data. It's easy for you to just know what I'm asking you and be able to pull those values out for me. The places where we tend to have the most mistakes are these conditional probability problems where you've got that bar saying given that, or the problems that have the or in it. We sometimes forget to do the subtraction. Those tend to be the bigger places where the mistakes occur. Okay, now we're going to move on to some tree diagrams, and I still have a formula here called the multiplication rule. And again, it's not a formula that I prefer to use, but I'm giving it to you for the sake of giving it to you. In my math class, the male-female ratio, I'm going to tell you in a particular class, is 17 to 23. We're going to choose 2 people at random and assume that the first person chosen is not allowed to be chosen a second time. They will be different people. Find the probability of choosing a girl first and a guy second, and then I want you to draw and label a tree diagram. Okay, what do we have here? A branch that tells me I have to make a choice, and I'm going to say we're going to either choose a male or a female on that first draw. Now, we've got the ratios. I know that there are 17 males out of the 40 people. So I'm going to write 17 over 40. And that 40 comes from adding the 17 and 23 together. And there are 23 out of the 40 women. And so the probability is 23 out of 40 that we take that bottom branch. Now, after we have chosen a guy out, there technically are only 39 people inside the class to yet be chosen. And I can still choose a male or a female on the second draw. Now, if I chose a male the first time, there aren't 17 any longer. You only have 16 males out of the 39 people. But again, if we chose a male first and now we're going to choose a female, all 23 females are still there because we chose a male the first time. If we chose a female on the first person, then we can either choose a male or a female on the second drawing. And again, the denominators will be 39 because the first person cannot be chosen a second time. If we chose a woman, Okay, there had been 23, but one of them was selected. The female count is down to 22, but we still have all 17 men. So the sample space for this problem would be man followed by man, man followed by woman, okay, woman followed by man, or woman followed by woman. Okay, now, if you want to find any of those probabilities, let's say we want, it says find the probability of choosing a girl first and a guy second. Girl first says, okay, let's do that one right there. And then a guy second, we're going up the branch to get to the male, and we want to know what's the probability of female followed by male. Well, in this structure here, you are going to multiply those probabilities together. 23 over 40 times 17 over 39. Now, the formula up above says probability of A, probability of the first thing. Well, that's really what we just did. And then the probability of B, the second thing, given A. The given that is we've gone down, we've done A, now we're moving up to B. So the second thing that you're multiplying is a conditional probability based on that we drew a female first. So yeah, you're using the formula, but it's a lot easier just to use counting and understanding what is going on that way. Now, when you go through to do your multiplication here, those are some big numbers, and I don't see any reduction possible here. So I'm going to use my calculator. So here we go. Let's go to our calculator. I still have some numbers from the previous video stuck in there, and we're going to just type it as we see it. 23 divided by 40 times the next fraction, which is 17 divided by 39. Now I could hit enter and get a decimal answer, but I'd rather get a reduced fraction. So again, I'm going to hit math, enter, enter. And there's my reduced fraction of 391 over 1560. Okay, let's take a look at our next problem. Now we've got our typical marbles in a bag problem, and I'm going to do this one a little bit differently. Let me draw a bag. We've got a bag with 3 red and 4 white marbles in it. So here we go with a bag. I'm going to write 3R and 4W. Okay, we're going to choose 2 marbles out one at a time. And we're going to draw a tree diagram both with replacement and without replacement. So the first time is with replacement, and over at the right we'll go without replacement. So we have red and white marbles, and so the first draw can be red or white. The second draw can be red or white. Now, the probability of going upward to red on the first draw would be 3 out of 7. The probability of going down to white on the first draw would be 4 out of the 7 marbles. Now this time it says with replacement, meaning all 7 marbles remain in the bag. And so the probabilities going upward are going to remain 3 out of 7 to go up to red, and 4 out of 7 both times to go down to white. Each draw, we say, is independent of the previous one. Now in this second drawing, again, I'm starting with this bag. Let me redraw that here because of that little squiggle we got in it. We're starting again with this bag that has 3 red and 4 white in it. And for the first draw, when we go to red or white, again, the probabilities are 3 out of 7 and 4 out of 7 respectively. But I'm going to redraw the contents of my bag at this point. Okay, if we drew a red the first time, we're down to 2 reds, but we still have all 4 whites in the bag. If we drew a white the first time, we still have all 3 reds, but there are only 3 whites. It's been reduced. So when we go to draw out the rest of our tree diagram, and we still will have the options of red or white on the second draw, now the denominator is going to change to 6 in each case, because there are only 6 marbles left in the bag because we did not replace the marble. And then we've just got to count how many of each color there are. So we have a 2 out of 6 probability to go up to red, and a 4 out of 6 probability of going down to white if red was the first marble chosen. And if the first marble chosen was a white going downward, we're going to have 3 out of 6 for each of those. And yes, I know that a lot of these fractions can be reduced, but I wanted the emphasis here to be on the values themselves. Okay, it asks you this question: what is the difference between independent and dependent trials? In independent trials, the outcome of one draw or one trial does not affect the next trial. And that's what we had at the left here with the replacement between draws. When you have dependent trials, then something is happening where the second draw or the second trial depends upon the outcome from the first trial, and the denominators are actually going to change in that case. Okay, dependent, the probabilities change. Independent, the probabilities stay the same from trial to trial. Now we have a word problem that kind of introduces a whole different concept to you. It says the probability that an Avon salesperson sells beauty products to a prospective customer on the first visit is 0.4. If the salesperson fails to make the sale on the first visit, the probability that the sale will be made on the second visit is 0.65, 65%. The salesperson never visits a prospective customer more than twice. What is the probability the salesperson will make a sale to a particular customer? Okay, I've got a branch started here because even though you might be able to do this in your head, sometimes it's often easier to have a tree diagram drawn out for you. So I'm going to do the following. I'm going to say that on the first attempt, there is either a sale or there is no sale. Those really are the two outcomes. And we were given the probability of a sale on the first visit was 0.4. Well, we know what the probability will be down here for no sale, don't we? That's going to be 0.6. Why? Because these are the only two possible options, and they're going to have to add up to 100% or 1. So I started with 1, I subtracted that 0.4 to get 0.6, which is the complement. Well, if I make a sale to this person, I'm done with that person. Yay! But if I didn't make a sale, I try again with that customer, or I don't, but the Avon rep does. So on the second trial, we're either going to have a sale, or again, there will be no sale at that point. So there's two possibilities here. Now it says, if they fail to make the sale on the first visit, the probability of the sale will be made on the second visit will then be 65%. And down below, you know, we can label this as 35% or 0.35 because those two branches again are going to add up to 1 or 100%. Now the question is asking, what's the probability the person will make a sale? Probability of a sale. Well, I'm looking at this as, oh, there's two ways that that can happen. That's the probability of a sale on the first attempt, which I'll call sale 1, or a sale on the second attempt. Okay, well, or is going to turn into addition. So I've got the probability of a sale on the first attempt plus a probability of a sale on the second attempt. And I know I'm writing this out in longhand, but hopefully it makes sense to you. I'm sure you can skip some steps in here if you wanted to. Now, the probability of a sale on the first event, we know is 0.4 or 40%. Okay, plus, now the probability of a sale on the second event, a lot of people write down 0.65 there. And if you do that, you say, oh, okay, great, I'm done. But you add these together and you get 1.05. And at that point, you go, womp, womp, womp. Something is wrong here, okay? You cannot go over 100%. And I'm going to tell you that that probability of 0.65 is not correct. Because in order to make a sale on that second attempt, you had to go through a failure first to get there. So technically, this is going to be 0.6 times the 0.65. That becomes 0.4 plus 0.39, and we have a final answer here of 0.79. So you've got to be careful here. You fall into the trap of conditional probability on this. And anytime something is specifically being done on the second trial, you have to take the first trial into account. Okay, now the reason I know the first trial was taken into account to get that 0.65 is it says if they failed to make the sale on the first visit. In other words, if we went down the branch, then the probability on that second branch was 0.65. So this is a little bit more challenging, and there's a lot you have to pay attention to, and that's why I'm going over these with you. Now, this same idea is going to take place in this next example. In the game of Parcheesi, each person rolls a pair of dice, that'll be the 6-sided dice, on each turn. In order to begin the game, you must either throw a 5 on at least one of the dice, or a total of 5 on the 2 dice. Now I've got the diagram shown here that you had in your notes where, that you have here, that lists all the different outcomes here. Now, if you throw a 5 on at least one of the dice, that means you're in the 5 column, or you're going to be in the 5 row. That's a way you can start the game. But it says, or a total of 5. Well, I've got a few places where a 5 shows up inside the table. So everything that I have just circled there is one of the ways that you can start the game. So what is the probability you start the game on your first turn? Well, let's count how many out of the 36 numbers I've circled. Going up the diagonal, I've got 1, 2, 3, 4. Then going down this 5 column, I'm going to have 5, 6, 7, 8, 9, 10. And then we have the row, 11, skip over the 10, 12, 13, 14, and 15. So I'm getting an answer here of 15 out of the 36. Now that is divisible by 3 over 3. So that will be 5 out of 12 is the probability that I start the game on my first turn. Okay, now it's asking what's the probability I start on my second turn. Well, if you were looking at a tree diagram and you said, okay, first turn you either started or no start, just like we had with the Avon sale or no sale. And then we said, okay, I've started, but I didn't start on the second one, so now I'm going to try again, start or no start. I'm interested in the start up here, probability that I start on my second trial. Well, if I had a 5 out of 12 chance of going up to start on my first trial, that meant the other 7 out of 12 chances mean I'm not going to start on that first turn. But then to go up to roll on the second time, now again, I've got a 5 out of 12 chance of then starting. So my probability is going to be 7 over 12, that is the failure on the first roll, multiplied by 5 out of 12 from this second roll. And so we are going to get 35 out of 144 as that answer. Let me make a point out of something that I haven't emphasized previously. Anytime you are going through these tree diagrams, you're doing one event and then another event, you are multiplying the probabilities together. In fact, in any problem where you can insert the words and then, that tells you to multiply. Roll the die one time and then roll the dice again, multiply those two probabilities together. Now, I don't have it in your notes, but I added on an extra part here because sometimes I believe we learn by exaggeration. If I wanted to find the probability we started on this 5th turn, that means you're going to have to go through 4 failures in a row, each with a probability of 7 over 12. And then it will be on the 5th turn that you will have 5 out of 12 chances to win. And so we'd have all these fractions to multiply together to find the probability that you would start on the 5th turn. I'm not actually interested in what the answer is there. I'm interested more so in understanding that process. You had to go through 4 of the failures before you get to that success on that 5th trial. Okay, so hopefully you're seeing a similarity between that Avon problem and this problem here, especially in how I've drawn the chart at the bottom left of this picture or of this screen. Okay, next problem here. A coin is being flipped 6 times. I want to find the probability that at least one of the flips will contain a tail. At least one. That means one or more of the flips will contain a tail. Well, wow, there's a lot of ways we can do this, especially if we start drawing a tree diagram and we say, here's my first flip, heads and tails. But then I'd have to have a second flip, a third flip, a fourth flip, and you can just see how many branches we'd be getting there. So that is not an effective way of doing this. And I don't even want to consider drawing a tree diagram. So something that you learn quickly is the opposite of one or more is none. If you got one or more, the opposite is none. So the opposite of this is getting all heads. So if I can find the probability of all heads, we're in business. Now that would be the 1 minus the probability of heads, 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 like that. And that becomes 1 minus the probability of 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 yet again, because every time you flip a coin, it is an independent trial, and each time you have a 1/2 chance. And I know that those are multiplied together because I'm flipping a coin, getting a heads, and then getting another heads, and then getting another heads. Each of those and thens say multiply these probabilities together. So in this case, I would have 1 minus 1 out of 64, which gives me 63 out of 64. Just a couple little comments here to help you. That 1 can be thought of as 64 over 64 if you want a common denominator to subtract, and that way you can see the 64 minus 1 making the 63. Now, another thing I'm calling to your attention here is the opposite of x greater than or equal to 1. That's a 1 or more, is x equals 0. Those are basically opposites when you're not dealing with negative numbers and you're just dealing with whole numbers. 1 or more successes, the opposite is none of them. So that's something to kind of stick away in your memory. Some of the tutors have told me that that's a concept that they try to stress because it's a place where students tend to have some difficulties. Okay, let's do a few more practice problems here. It says if a person is randomly selected, find the probability that his or her birthday is on October 18th, which is National Statistics Day in Japan. And it says ignore leap years. Okay, well, basically that says we're dealing with 365 days in a year, of which October 18th is one of those days. And we're going to say 1 out of 365. Now, I decided to throw in for you another part of this of paying attention to leap years. Now, since when you're dealing with this, you can't just look at 1 year. Some years have 365 days. 1 out of every 4 has 366 days. With the addition of February 29th, you sort of need to look at a 4-year spectrum. Every 4 years, there will be 4 birthdays. So what I did is I said my numerator is 4 birthdays every 4 years. How many days are there in 4 years? Well, you've got 365 days for 3 of those years. And then on that 4th year, you have 366. So that gives you the total number of days in 4 years. And each of those years, there will be an October 18th. And so there will be 4 of those days. So that would be how you would handle including the leap years. Now, if I'm dealing with choosing a person at random, what's the probability his or her birthday is in November? Again, we're out of 365. You need to know that November has 30 days in it, 30 out of 365. Both of them are divisible by 5. I know because they end in 0 and 5. And so that can reduce to 6 out of 73. If you want to pay attention to leap years, now again, I go to that 4-year perspective. And in the course of 4 years, you will have 30 days in November for each of those 40 years. So I know that the numerator will be 120 out of grand total, again, 3 years with 365 days in it, added to 1 year that has 366 days in it. A couple more problems. Part C, problem C. After collecting IQ scores from hundreds of subjects, a box plot is constructed with this 5-number summary. Okay, 82, 91, 100, 109, and 118. If one of the subjects is randomly selected, find the probability that his or her IQ score is greater than 109. Okay, well, 109 is one of those numbers that was given as part of the 5-number summary. And that refers to Q3. Remember how we had the minimum value, Q1, the median, then Q3, then the max. Well, what I did is I drew a little box plot for ourselves, and I reminded ourselves that Q3 is going to be at the right edge of this box. So I want to know what's the probability that the person's IQ is greater than 109. Isn't that just referring to that top whisker there? And we know that in that whisker, there's going to be 25% of the data values. Finally, we're asking what is the probability of getting 4 consecutive aces when 4 cards are being drawn without replacement from a shuffled deck. Okay, well, let's think about it. A shuffled deck, we begin with 52 cards, and there are 4 aces to choose. If we choose an ace, there's only 3 left, but then we're down to 51 cards. And then there are 2 left out of the 50 cards, etc. So what I've done is I've listed these out. There's my 4 out of 52, dropping down to 3 aces left out of 51, and then 2 out of 50, and then 1 out of 49. And then I decided I'm going to go and do some canceling along the way, which you don't need to do if you're going to just let the calculator do all this for you. I let the calculator do this for us, and I can tell you that your probability of getting 4 aces dealt to you in a row is 1 out of 270,725. Okay, very slim chances of that actually happening. Now let's do one final topic, and that is about how to generate random numbers on your calculator. So let me open up my calculator. I'm going to let you read this one on your own. Basically, you need to do something which is a one-time only feature on your calculator, and I want everybody to do something different here. I want you to just start typing in some number. Whoops, I don't want any addition in that. Let me try that over again. But just type in some old number, and you don't want the same number as me. What we're going to be doing is we're going to be setting a seed here. I want you then to hit your store button, which is the one that's showing red on my screen down in the bottom left corner. When you hit store, you get a little arrow on your screen. Now, what that's going to do now is it's going to allow you to store whatever number you typed in into a memory location, which is going to be called rand, for random number. Now we're going to hit the math button, which just turned red. We're going to move over 3 columns to the right to probability, and that first choice there is rand. So hit enter, and then hit enter again, and it will put that number there. Now, the reason we do this is your calculator is programmed with a seed when it comes out of the factory. And so if you all have brand new calculators and you create a random number, you'll all get the same number coming out of it, which is no fun. But if you set your seeds to different places, then it's going to appear to be random because everyone's going to be starting in a different place. Okay, that's basically what's going on right there. Now, that is a one-time thing. That seed location will continue to advance as you use random features on your calculator. And as you turn your calculator off and then turn it back on, those numbers will still be there. Okay, the next thing I want to show you deals with the rand int function. Okay, if I hit my math button again and go over to probability, and then I go down to rand int, which is choice 5, I will need to enter a lower bound and an upper bound. So let's pretend I want to roll dice. I'm going to have 6 numbers on a dice ranging from 1 through 6. And if I want to pretend I'm rolling 2 dice, I will type in the number 2 there and move down to paste. Now, if you don't have this menu, not to worry. What you're about to see on this screen is what you would be typing in. When you hit rand int, you get an open parentheses, and you just say, I want my number to be from 1 to 6, and I want it to be rolled twice. When I hit enter, it just rolled 2 dice for me. I rolled a 1 and a 5. And what's nice is if I want to do it again, I don't have to go and find it in the menu again. I can just hit enter. It just rolled double 1s. It just rolled a 4 and a 2. It just rolled double 1s again. Wow. And then a 3 and a 1 and a 6 and a 1, etc. So bottom line is you can use this to generate random numbers. Being a little bit of a geek, I'll tell you something that I've done at parties. I'm going to go back into this feature here to probability down to rand int. And let's say I've got 6 people or 10 people, and we want to choose someone to go first in a game. What we do is I'll just say, oh, there's 10 people here. Let's just go from 1 to 10. Let's just choose one person, and we'll designate who's number 1, and we'll go around the circle and call off numbers, etc. And right here, that'll tell me person number 3, you get to start the game. So I thought I'd show this to you just to kind of finish off the chapter on probability for you as something that you can do on your calculator that's a little bit out of what we've been doing so far in this chapter. So I'm going to wish you guys good luck on this, and we'll see you back on the next video. Okay.